Hello, everybody. My name is Alan Coley, and the talk today is on geometric horizons. And in the talk, as you can see from the abstract, I'm going to try to do a couple of things. A very, very brief introduction, overview of geometric horizons, what I mean by a geometric horizon. And secondly, two aspects, two areas of current research that I'm interested in. The first is theoretical, and the second is application of some of these ideas to numerical integration of the merger of black holes. Here are some useful references from which the talk is taken. Okay, so within black holes, the theory of black holes, there is an event horizon which characterizes the boundary of the black hole. Event horizons are notoriously difficult to compute, and in practice, people try to find quasi-local definitions of black holes, or the boundaries of black holes, and in particular something called apparent horizons. So these are used, for example, in numerical studies of black hole mergers and so on and so forth. So we start off with the idea of a marginally outer trapped surface, which is a two-dimensional surface, spherical topology, in which the expansion of the outgoing null vector, normal to the surface, vanishes. So the outgoing expansion is zero. The expansion of the ingoing null vector is negative, so it's a trapped surface. And these so-called MOTs evolve in time and can form three-dimensional surfaces called marginally trapped tubes, MTTs. And effectively, if they form in an appropriate way, a nice smooth way, this forms what's called a dynamical horizon. What we're more interested in is the idea of an apparent horizon, which is the outermost marginally trapped tube. Unlike the event horizon, these apparent horizons, I'm going to effectively be talking about MOTs the whole time, but I'm going to use the word apparent horizon interchangeably, quite wrongly, of course. These are quasi-local, and they can be used in black hole mergers. One problem is that the notion of apparent horizons and MTTs are foliation dependent. So if you actually divide the space-time into, say, or you foliate into 3+1 classification, then the apparent horizons depend on how you choose your time-like hypersurfaces. And as I say, these have been successful. This idea of apparent horizons has been successfully used in black hole mergers, and there's a lot of current work being done by various people on understanding apparent horizons better, MOTs, MOTs, and apparent horizons better. So what I'm concerned with, or have been concerned with for some time, is to try and have a more geometrical approach to this problem. And I've, together with some colleagues, have defined a notion of something called a geometric horizon, in which the horizon is defined by the fact that the curvature tensor or its covariant derivatives are algebraically special on these horizons, on these surfaces. This is a purely geometrical concept, and can be these surfaces can be determined by curvature invariance. So this is if you like, an alternative way to look at the problem. Algebraically special in this sense is to do with the fact that there's a null vector with certain algebraic properties, so that the curvature tensor, for example, is algebraically special with respect to something called a boost weight, a choice of boost weight of the various, a choice of null frame. and that the condition that there is a horizon is determined by the fact that on these surfaces the algebraic properties of the space-time is more special. I'm stating this as a conjecture just for something a little bit more concrete. Conjecture part one: for space-time, if you have a space-time that's arising in the merger of real black holes, typically the geometry is algebraically general away from the horizon, but on the horizon it's more algebraically special. So in the case of a collapse where you expect the space-time to be algebraically general, the horizon, the surface, is actually determined by the algebraic type being special on that horizon. And the important thing is, the reason why progress can be made using this type of notion is that recently it's been proven that these algebraic alignment conditions, these special conditions for it to be algebraically special, can be determined by the vanishing of certain scalar polynomial curvature invariants. So therefore these surfaces, which are being defined as being algebraically special, can be located by the vanishing of the zeros of scalar polynomial curvature invariants, which of course are not dependent on the space-time foliations. I should make a comment here that this is not really a conjecture per se, it's an idea that the algebraic, the condition of algebraic specialization can actually determine this surface, which may play an important role, perhaps even substituting in for the idea of an apparent horizon. It's a suite of conjectures because in different circumstances, the role of the curvature is different. So, for example, for stationary space-time, it can be proven that this geometric horizon is in fact the same as the horizons that are normally considered in exact solutions. But in the exact solutions, the spacetimes are often algebraically special to begin with, for example, type D. So we actually have to look at the classification of the covariant derivative of the curvature in order to identify the horizon. So it's a suite of conjectures in the sense that not only the curvature, but its covariant derivative is algebraically special, which identifies these spacetimes. This final comment is that if we're dealing with 4 dimensions, the Val tensor's algebraically general means it's something called type 1. It already has a specialization, and so therefore it has to be the horizon is determined by the condition that on the horizon it's at least type 2 specialization. It means it's type 2 or type D. Now these conditions for it to be algebraically special can be given in terms of scalar curvature invariants. In the case of 4 dimensions, the Val tensor is the condition for the Val tensor to be of type D is determined by 2 real conditions. In 4 dimensions, these 2 real conditions are equivalent to the real and imaginary parts of the complex quantity D in terms of various Newman-Penrose quantities being 0. I mention this because this is the route we're going to take, or I'm going to take in future analysis. So in 4 dimensions, for the Val tensor to be of type 2, algebraically special, there are 2 real conditions that need to be satisfied, completely equivalent to these conditions here. If I were to look at the covariant Val tensor, the covariant derivative of the Val tensor, there are conditions in terms of scalar curvature invariance for it to be algebraically special. If I were to look at higher dimensions, there are real conditions in terms of scalar curvature invariance for it to be algebraically special. In the particular case of type 4 dimensions and the Val tensor, they're completely equivalent to very familiar conditions in terms of the complex vowel tensor. Here are the conditions here. For what it's worth, if people know these things, they'll recognize this. And so this is what we would be studying for a general collapse to see where these invariants are zero. Here's the comment concerning what I said a moment ago. If, however, the spacetime that we start off with is zeroth order algebraically special, that is, the vowel tensor is already algebraically special, then this horizon is located by the fact that the covariant derivative of the vowel tensor is zero on this surface. So that's the background. The basic idea is by looking at the algebraic specialization of the vowel tensor, which can be determined by curvature invariance, we can actually locate these special surfaces. And I guess the motivation is twofold. One is that it may be a useful thing to do to look at the geometrical content of the spacetimes to see whether the curvature invariants give us useful information. And secondly, whether something like a geometrical horizon can be determined that will be a useful idea. The problem with the approach is, now this is not necessarily true in the case of exact solutions. If you have an exact solution, you can often calculate the scalar curvature invariance precisely. But if you were to be looking at more general situations where we need to calculate the zeros of scalar curvature invariance, it's very, very difficult to do. And so there's immediately a problem of practicality in the sense that even though we have a well-defined method for studying these so-called horizons, it's very impractical in general situations. However, the fact that the algebraic the spacetime is algebraically special means that there's a preferred frame, which is called an algebraically preferred null frame. That's what I'm calling it here. The algebraic nature of these null vectors plays a central role, and it suggests perhaps a slightly different approach to this problem, which may be more practical. And this is the first thing I'm going to talk about in a moment. There are two aspects to this. One is that we want a way of actually calculating these invariants, and as it says here, this may be best done through something called Cartan invariants rather than scalar curvature invariants, which are equivalent to scalar curvature invariants in black hole spacetimes. And we want to show that the Newman-Penrose quantities are related to the algebraic specialization of the covariant derivative. So the first application. So the basic idea is to study the curvature of spacetimes in black hole collapse, black hole mergers, and see whether these invariants tell us something interesting. In particular, to see whether any of this notion of a geometric horizon is a useful concept. The first aspect of current research is trying to make this a little bit more practical so it can actually be applied in physical situations. Now, I've already mentioned that in order to determine whether a spacetime is algebraically special, the way it's chosen via boost weight is to look at a null frame with null vectors, and these null vectors have special roles and can be chosen in a certain way so that their algebraic properties are explicit. So we start off with a null tetrad. In particular, we have two real null vectors, L and N. And if it's algebraically special, it means that the so-called boost weight plus two terms of the vowel tensor are zero, which means that, let's say, L is preferred. And if we choose the preferred value for L, then the space-time will have no boost weight plus 2 terms, and the algebraic type of the space-time is explicitly of type 1. This means that we're looking for surfaces in this null frame for which the tensor is type 2, so the various boost weight terms are 0. Namely, in terms of Newman-Penrose, psi 1 is 0. So the first step is to notice that the way that we've defined algebraically special is algebraic and depends on the choice of a null frame. And so one way of exploiting this is to actually take a frame approach to the whole problem. We want to show, of course, that these frames in which it's algebraically special, or these surfaces which are algebraically special, have some physical properties which we should do through invariance. And there are various Newman-Penrose coefficients that we're going to be particularly interested in. In particular, there's one called rho, which is in fact related to the expansion of the null direction L. So L is not only special, rho characterizes whether its expansion is vanishing. So presumably what we'd like to do is to show that for one of these surfaces, geometrical horizons, that rho is going to have zeros on the horizon. We want to choose the frame completely in an invariant way. So we employ the Cartan-Karl-Healy algorithm, so that once the fix is complete, the frame is completely fixed, all of the various quantities left are Cartan invariants. And so therefore we can study these Cartan invariants rather than scalar curvature invariants, which is computationally is much more simple. This preferred frame, we want to set psi 0 is equal to 0, so you want to choose the null vector L in an appropriate way. We can use this is done by null rotation, 2 degrees of freedom of the Lorentz freedom. A spin can be used to show to construct a real psi 1, so that the spacetime is now in this frame algebraically special when psi 1 real condition is equal to 0. And then in order to fix the frame completely, we have some additional conditions that need to be satisfied. The way we choose the APNF, so this is one aspect of current research, that is, we want to try to define a preferred frame, an APNF, so that we can identify the special surface, the geometrical horizon, through the vanishing of various Cartan invariants. In particular, the real part of psi 1 being equal to 0 identifies the horizon. The choice of the APNF that I've presented here is a particular choice. This particular choice is useful because you can actually prove some interesting results in this frame. Namely, you can argue that when psi 1 is 0 on this surface, when psi 1 is 0, rho is automatically 0 on this surface. So the surface's psi 1 equals 0 does in fact have some physical properties which are related to it having some properties of a trapped surface. So there's some arguments that sort of indicate this is the right way to go. In more current work, we're looking at the possibility of choosing the null frame, not so much in this way. We would have still that it's algebraically special, so psi 0 is 0. We would have psi 1 is real, and it's more practical to choose psi 4 to be 0, and the final condition for the fact that psi 3 would then be complex. physics. So the way that we're actually envisaging applying this is slightly different to the way it's been presented here, for more practical reasons, so that we can actually find the frame a little bit more easily. There are examples of where we might be able to use these or justify the use of these definitions. So if we present these so-called GH conjectures, there are examples that perhaps support the notion of these things being useful. And in particular, we want to show that if we have a particular horizon, that it has some physical properties, such as this coefficient rho is 0. The examples consist of stationary spacetimes. These are spacetimes which are exact solutions. You can actually prove things for. Unfortunately, they're typically type D spacetimes, and so the horizon is determined by the covariant derivative of the Weyl tensor, and they are located by rho being equal to 0. In the dynamical cases of spherically symmetric dynamical black holes, or non-spherically symmetric type D spacetimes, we've been able to show that the horizons, the physical horizons, are associated again with this Newman-Penrose coefficient being 0. A fourth set of examples come from a set of exact solutions. These are the so-called Kasner-Trashan spacetimes. These are four-dimensional non-vacuum, there's an electromagnetic field, equal mass black hole spacetimes. These have the advantage, of course, they're artificial, because to find an exact solution, there has to be some degeneracy between the various constants in the problem. Namely, the curvature has to balance with the electromagnetic field in this case. They're always artificial, but they're exact solutions, so you can actually do some analytical work. We looked at these examples to see whether such spacetimes admit a geometric horizon, and we adapted the frame. But because the tensor, the Ricci tensor is non-trivial, we actually adapted it to a Ricci tensor, not the Weyl tensor as indicated here. And we showed that the vanishing of rho does in fact characterize a geometrical horizon. We look at the case of two black hole masses in which they don't exceed a critical mass, so that we actually get black hole coalescence. In the in the non-subcritical case, they actually don't coalesce. So this can be used for analytical calculations and an illustration of the method. This is the metric of the Kasner-Trashan solution. The quantities here are defined by this quantity here. The particular case we're looking at is the subcritical case, and so there's some conditions on the parameters. The electromagnetic field is non-zero. We find that the Ricci tensor is of type D in terms of the algebraic boost weight decomposition. If we choose our frame adapted to the Ricci tensor to define our APNF and look at the Cartan-Kalhidi scalar invariance, we can show that rho equals 0 in this frame defines the horizon. In this frame, this is what the various quantities are defined. The one forms here, and here's our null, a choice of null vector before we've actually adapted it to the Ricci tensor. So in previous analysis, we actually showed that adapting the Ricci tensor to this frame, we can identify the horizon with rho is equal to 0, which is promising. But this is a very artificial example, and we would like to at least be able to reproduce these results with the frame adapted to the Weyl tensor, which will be a precursor to looking at more general black hole merger spacetimes. Here's a very brief overview of how you do the adaptation of the frame. So this is basically the algorithm, if you will, for finding this preferred frame in which to do calculations. This is a null transformation. E is a complex quantity. Under a null rotation, the spin coefficients transform according to this. So if we choose E to be a root of this equation, then applying this null rotation makes psi 0 equal to 0. So this is a little calculation just showing you how to do that. Non-trivial, but straightforward. The original frame, in the original frame indicated a moment ago, the Weil tensor has these components. So in the new frame, we would actually boost the frame and calculate the quantities, the Weil spinor components in the new frame in terms of these components here and the solution for E. So in this new frame, psi 0 would be 0. Here we are. High tech. And the remaining quantities would transform according to these rules here. If we want psi 1 to be real valued, we choose a spin, so that a real spin, so a Lorentz degree of freedom, so that psi 1 is real. And then in the previous definition, we then chose psi 3 to be 0, so we do another rotation with respect to B. Solve this equation and then solve this equation here. So we completely fix the frame. There is indications that in this frame, when psi 1 is equal to 0, we have the row 0, and this actually characterizes a horizon. The reason we're doing it for this particular example is that some of this can be done analytically, and so we can actually have a method for computing or checking numerical procedures for finding solutions when we actually look at a real situation. So the first application is theoretical, to try and find a method for attacking the problems. And the argument is that by choosing a null frame, this is a practical way of going about business, and that this is a suggestion for how the frame should be chosen. And so the question now is to see whether by choosing this frame we can actually show, at least for some simple examples, for example the Kasner-Trashin solution, that we are indeed locating a surface which could be called a horizon. But obviously we want to look at more realistic black hole mergers, which must be done numerically. There has been some work done on the case of the axisymmetric head-on collision of two unequal black holes. Here is the conventional references to work in this area. And here is a very brief description of the situation that occurs in this black hole merger. And we revisited this problem in terms of in trying to use curvature invariance, and got some relatively positive results. Let me turn immediately to a second example, which is a little bit more interesting. That is merging non-axisometric binary black hole merger. So this is ongoing work now. We, meaning myself, Jeremy Peters, and Eric Schnetter, have studied numerically the curvature, the invariant curvature invariance, by looking at the zero sets of the magnitude, which is real, of the complex scalar curvature invariant D. So we've studied this quantity here, a real curvature invariant, in or through the quasi-circular merger of two non-spinning equal mass black holes numerically. And the numerical results are encouraging. And I'll show you the pictures in a second. The numerical results are encouraging. What we need to do, though, is to make a stronger case that the surfaces we're determining are of physical interest. So we need to be able to discuss what the values of this Newman-Penrose coefficient rho is in a preferred frame. The diagrams, I'm going to just show you some pictures just to describe what's happening, just to perhaps give you a little taste of what's going on. Some information here. The data was provided by Eric. The actual graphs were made by Jeremy. So this is just a quick look at what happens in this particular case. There are going to be some snapshots at early times, which is t equals 8 when the two black holes are still distinct. Intermediate times when they're beginning to merge, which is characterized by t equals 16. And at later times once there is a horizon shared by both black holes. And we do it by looking at the so-called level epsilon curves. That is where the magnitude is equal to a very small number, and various level curves for different values EI are actually calculated. So we're looking at the level sets, the level epsilon sets. These are sets where this absolute value of D is equal to a very small number, and we're mapping them. So going to the diagrams. So this is a description of diagrams. Let me try to describe what's happening. So this is two rotating black holes. They're equal mass. You see that the center of these things is going to process as we look at the different pictures. This is a snapshot at t equals 8, where we start the integration off at t equals 0, where the two black holes are distinct. These are the contours of the level 10 to the minus 3 sets, i.e. these surfaces. The white curve is a curve where the absolute value of D is equal to 10 to the minus 3. There are subsequent level sets which are smaller. This one is 5 times 10 to the minus 4. The green one is 3 times 10 to the minus 4. So the colors going from white to green means that D is actually getting smaller. And you can see that the white level sets, where the absolute value of D is 10 to the minus 3, is given by this contour here. And at this time here, this surface completely, or there are two surfaces, each of which completely envelop the black holes. I should say that these, of course, are snapshots at various hypersurfaces. So this is the snapshot where one of the coordinates is equal to a constant. So this is a constant hypersurface snapshot of the solutions. The actual horizons are, of course, three-dimensional and spherical in topology. So you can see here the nature of the curvature invariant, which is interesting in its own right. You can see there is some structure there, and you could argue that looking at the value of this curvature invariant can be instructive. In the second picture here, the blue dot is the centroid of the black hole, and these blue curves is curves of the apparent horizon calculated from by other methods. The blue circular surface is the average value of the apparent horizon, or MOTS, and the light blue is the exact one, but which is approximately spherical, or approximately circular. So the blue curves tell us where the apparent horizon is, and you can see that the white curves, to some extent, capture the behavior of the apparent horizon. So these curves, level epsilon sets for epsilon small, seem to be capturing some of the information of the MOTS around the black holes, the two individual black holes at this time. So this is somewhat encouraging. We go to a later time to see what happens. Now, of course, the two have rotated relative to each other. Again, we have this picture here where these are the level sets. Here we got the white ones are the same, the 10 to the minus 3 level sets, and then the red and the green as the level sets get smaller, or the values of epsilon get smaller. You'll notice that as time increases, there's still two closed curves enveloping the black holes, but there are now sets of points in the intermediate region that are forming, giving the level sets, let's say, for example, the white level sets where D, the absolute value of D, is equal to 10 to the minus 3, has this extra structure here. So this is actually the dynamical region. Here's the white one where the smaller value is closed curve. The red and the green ones you can see are a little bit less easy to define. Again, we have the relative, for comparison, we have the apparent horizon to see what's actually happening. The apparent horizons have not actually, there's no new MOT that's formed yet, but the curvature is indicating some dynamics. What these other two quantities are is one has to be careful, because what we're seeing, or what we see in these pictures, is the structure of the curvature of the scalar curvature invariant we've plotted, which does indeed have some structure, but eventually we're going to want to try to interpret this. And of course, these are level sets where D is not 0, but D is very small, or the absolute value is very small. Now, unfortunately, because we've taken the absolute value of D, this is a positive definite quantity. So if you're doing numerical analysis, any numerical error will always give you a positive value for D. It will never be 0. So the best we can hope for is D being small. Secondly, of course, if you have a finite grid and you don't actually have the grid points on the zeros, D, the absolute value of D, will always be 0. So we need a little bit more information about what these curves are telling us. And what's plotted here is two things. This one here, what happens is if we take a particular cut of the curvature, in fact, the curvature, the absolute value of D, is not monotonic. It actually has some local minimum. And these dots are plotting the local minimums associated with D. So although D is never 0, as D decreases, eventually D actually has a local minimum, and I've plotted the local minimum here, which perhaps indicated that there is something actually happening on these contours, perhaps indicating that there is a minimum in D, even though D is very small. And what's plotted here is the real part of D. Now, the real part of D is a real function. And of course, it's not positive definite, so it can change sign. So what we've got here is the light green is the level +1, plus 0.01 level sets. So the green sets have a positive value of dr. The yellow ones are negative minus 0.01 sets. So this is where dr is negative, and this is only plotted to indicate that dr goes through a 0. So there is at least an indication that as we go through a region bounded by the yellow curves and the green curves, that we do actually have a 0 of some description. At later times, this is what it looks like. By this time here, in this case here it's t equals 20, the structure between has disappeared, and we now have a single set enveloping both black holes. Again, we've got the white ones are the epsilon 10 to the minus 3 sets, and the green and the red ones are smaller sets. Again, we've superimposed the apparent horizons, or the MOTS here. Here are the two original MOTS around the individual black holes. By this time, the MOTS have bifurcated, and there's an inner MOTS and an outer MOTS. The inner MOTS is also indicated, and you can see that the inner MOTS is very, very roughly approximated by these contours. And there's an outer MOTS, which is the apparent horizon, which is actually not in view here. It's much larger. Here are the minima indicated here to show that this contour is also possibly showing a minimum in this quantity absolute value of D. And this one here is the level sets of the real part of D again, and it's a little clearer here that there is a change of sign, because the green contours are now a closed curve, not very dissimilar to the curves over here, and the yellow ones are inside, and you can see there is a region where it goes through zero, a bit more clearly than the previous one. So the conclusion is, firstly, by looking at the values of these scalar curvature invariants, we may be able to learn something interesting about black hole mergers. And there is a little bit of a hint that these this geometrical horizon notion may actually be quite useful, that we may actually be seeing surfaces which have the characteristics of an horizon. Clearly, this all depends on future research and doing and finding some more results. Thank you very much.